Hello students. In this video we're going to verify a vector calculus identity. We have the curl of a vector field here, and um, we're going to verify that that's equal to the gradient of this divergence here minus the Laplacian of the vector field. Now that's going to look a little strange to you. I'll explain what we mean by that towards the end of the video. You might be used to the Laplacian being a scalar quantity. I'll show you what it means to have the Laplacian of a vector field. In this verification, the vector field E is going to be broken into the components E1, E2, and E3. And recall that the divergence, grad dot E, is a dot product. So you have ddx, comma ddy, comma ddz in this vector, dotted with E1, E2, and E3. And so when you dot those two vectors together, you apply the derivative operators to each of the components of this vector. So you get de1 dx plus de2 dy plus de3 dz. Okay, so just a reminder of what the divergence is. We're going to have to recognize that later in this video. All right, so you may want to play along at home as we go through this verification. It gets there's a lot of bookkeeping. I'll do my best to try to help you keep it straight. Okay, so the first thing we're going to do is we're going to work inside out. So we're going to take the cross product, the curl, which is a cross product of this inner part. So we have grad cross E. So we just apply our mnemonic with the determinant. And here's the definition. This is just straight out of definition of curl. So notice it's the third component minus the second component, and that's in the I here. So it's d E3 dy minus d E2 dz. Okay, and then you could just follow along with each of those and just take a look at them. I'm not going to repeat what I've written here verbally. This is just straight out of definition of cross product. Now, what we're going to do here before I proceed is I'm going to distribute this negative sign, this -1, into this quantity here. That way I can keep my signs straight. So that means this middle component here is going to have a de1 dz minus de3 dx. All right, so keep note of that. All right, now we're going to take the curl of E, and so now we have this determinant, and we're just going to straight ahead apply that curl operator to the curl of E. Now what I'm going to do first here is I'm going to take a look at all the second derivatives that are not mixed. Okay, so notice that in the I component we're going to take ddy, and it's going to get applied to, okay, it gets applied to this term here, but that's going to give us a minus d squared E1 dy squared. That's this term here. Then I'm going to apply ddz to this term here, and notice we have an de1 dz, so that's going to give us that second partial here. Similarly, okay, I'm going to ignore the mixed partials just for a moment. We'll come back to them, okay, because I understand when we apply the dy, there's a d squared e2 dx dy. I'm going to come back to that. I'm just going to focus on the ones that are not mixed right now. Okay, and then in the j component, so we have the minus j. That means we're going to take ddx, and that's going to get applied to a d squared e2 dx squared plus, and then this is really nice, you apply it here and you get a minus minus, which gives you a plus, de2 squared dz squared. So notice how this is shaping up. Here we're taking the second partials with respect to y and z of E1. Here we're taking the second partials with respect to x and z, which is of the j component, so there's no y here, of E2. And then you could argue by symmetry. You can see that you're going to get E3, and then you're going to have x and y, the partials with respect to those. And you could verify that by just following along by doing the determinants in these two directions. Okay, so those are those partials. Now, next, we're going to have the mixed partials. Okay, so we cross out the I column in the top row, and then we have the d dy, and then here comes the mixed partial. It'll be e2 with respect to x. So that's e2 with respect to x. And then we go in the other direction, and we'll have the mixed partial minus, which will give us a plus, e3, and then with respect to x and the z. And then similarly, if you go along the j column, cross out the first row, the mixed partial will be xy, and the mixed partial here will be yz, and that'll be with the e1 component and the e3 component. And then similarly, the last one, that should be a plus k. I fixed that in a minute. It will be e1 with respect to xz, and then you go in this direction, and it'll be e2 with the mixed partial yz. Now I am playing a little fast and loose. I'm switching the order of these partials. I'm assuming that e is continuous in the it's continuous in the first derivative, and it's continuous in the second derivative. That's an underlying assumption. Okay, next. I left some space over here because I'm going to use an analyst technique, and I'm going to add and subtract the second partial of e1 with respect to x in this first component. And notice I fixed the plus k down here. And then I'm going to add and subtract the second partial of e2 with respect to y, and then I'm going to add and subtract the second partial of e3 with respect to z. Now you'll see why I do that in a moment, because I'm going to collect. Notice that I have the second partials of e1 with respect to y, z, and now x. Same thing, I have the second partials with respect to e2 of x, z, and now y. I will put that one. And then I have the second partials of e3 with respect to x, y, and now z. So I'm going to collect those terms, and then I'll show you how I collect the mixed partials in a moment. Okay, so I'm going to distribute this minus sign as I did did up here. That way I can keep the minus sign straight. And now notice that all these first terms in the sums, these first two terms, all have minus signs. Okay, so when I collect those, you can already start to anticipate that's where this minus Laplacian is going to come from, because remember the Laplacian is the second derivative of the vector field of each of the components. Okay, so now if I collect these green terms here, these red terms I've just underlined. So I've underlined all the terms in the Laplacian that I'm collecting. You notice I have d squared dx squared, d squared dx squared, and d squared dx squared there. And those got applied to e1, e2, e1, e2, and e3. e1, e2, e3. And similarly, for e1 with respect to y, e2 with respect to y right there, and e3 with respect to y, and then similarly for z. And then I factored out the minus sign right there. So this is the Laplacian. That's all these underlined terms, just the distributive property, and I just factored out the second derivative operator. Now ignore the underlined terms and look at the mixed partials. You'll notice in the first term each of them has a dx, and then a dx, dy, and dz. Okay, similarly for the j component, each of them has a dy, and then a dx, dy, and dz. And then in the third term, each of them has a dz, and if I factor out the dz derivative, I'm left with a dx, a dy, and a dz. And so we'll get something that looks like this. I factor out the dx in the I component of just the mixed partials, and I'm left with de1 dx, de2 dy, de3 dz. And that happens in every one of these components. I factor out a dy in this case, and I have a dy in this case. I have a de1 dx, de2 dy, and de3 dz. And that's what we have here. And similarly for the third component. Now this hopefully will look familiar. If you look up at the top, that is a divergence. That is the grad dot E. So I will just simply apply that. And what we have here is the Laplacian of the vector field E and that's what I mean by the Laplacian of that vector field, plus this is the gradient operator applied to this scalar field, so that's what that looks like. But that is just equal to the gradient, and this is the divergence term, grad dot E. And that is how you prove that identity. All right, good luck.